What specific problem does the Cascade method aim to solve in the context of LLM inference, particularly in relation to the vocab matching attack?
The Cascade method aims to address the security vulnerabilities associated with the vocab matching attack, which can decode input tokens from hidden states in large language models, LLMs. Specifically, the Cascade scheme introduces a multi-party statistical inference approach that employs token-level sharding to obfuscate hidden states, making it resistant to the vocab matching attack. Unlike previous statistical schemes that expose permutations of hidden states, Cascade ensures that the gaps between revealed token indices are sufficiently large, thereby increasing the computational cost for an adversary attempting to reverse the input tokens. This design choice significantly mitigates the feasibility of the generalized vocab matching attack, which relies on recovering tokens from known hidden states. Overall, Cascade presents a more efficient and scalable solution for secure LLM inference while maintaining a balance between performance and privacy.
How does the proposed Cascade method work? Please illustrate the methodology step by step, especially focusing on the token-level sharding process and its significance in the scheme.
The Cascade method operates through a multi-party statistical scheme that employs token-level sharding to enhance security and efficiency during LLM inference. First, the input tokens are divided into disjoint subsets, creating sharded hidden states, query states, and key-value states, which are distributed among multiple comp nodes and atom nodes. Each comp node processes its assigned shard of hidden states by applying layer normalization and projecting these to obtain query, key, and value states, which are then sent to the atom nodes. The atom nodes perform the self-attention mechanism using the received projections, calculating attention outputs, while ensuring that no single node has access to all tokens, thereby mitigating the risk of information leakage. Finally, the comp nodes aggregate the results from the atom nodes to reconstruct the output, maintaining a balance between computational efficiency and security against attacks like the vocab matching attack, as the gaps between token indices in the sharding process complicate potential reconstruction efforts.
Can you provide a simple example to illustrate how Cascade operates during the inference process, particularly highlighting the roles of comp nodes and atom nodes?
During the inference process in Cascade, the operation is divided into three main phases: the pre-pass, attention pass, and post-pass, involving comp nodes and atom nodes. For instance, consider a scenario where we have two types of nodes, comp nodes and atom nodes. In the pre-pass, each comp node receives sharded hidden states and computes the query, key, and value projections, returning these to the atom nodes. In the attention pass, the atom nodes concatenate the received projections from multiple comp nodes to compute attention scores and outputs, which are then sent back to the comp nodes. Finally, in the post-pass, the comp nodes aggregate the results from the atom nodes to produce the final output for that layer, effectively reconstructing the attention output while maintaining the security of the input data through sharding. This structured approach allows Cascade to efficiently perform inference while minimizing information leakage.
What are the theoretical and practical advantages of using the Cascade method compared to traditional SMPC schemes, particularly regarding computational efficiency and communication costs?
The Cascade method presents significant theoretical and practical advantages over traditional secure multi-party computation (SMPC) schemes, particularly in terms of computational efficiency and communication costs. Theoretically, Cascade is up to 100 times faster than existing SMPC schemes, as it does not rely on cryptographic primitives like additive secret sharing or homomorphic encryption, which often introduce substantial computational overhead. Practically, Cascade achieves over 150 times lower communication costs due to its token-level sharding approach, which minimizes the amount of data exchanged between nodes during inference. This efficiency is further evidenced by empirical results showing that Cascade's runtime is comparable to vanilla inference, with only minor increases attributed to attention score compilation. Overall, Cascade's design allows it to scale effectively to modern state-of-the-art LLMs while maintaining a lightweight operational footprint.
How did you validate the security and effectiveness of the Cascade method? What specific datasets, metrics, or benchmarks were used to demonstrate performance improvements over existing methods?
We validated the security and effectiveness of the Cascade method through a series of experiments that focused on its resistance to the vocab matching attack and learning-based reversal attacks. Specifically, we utilized the FineWebADO dataset to probe the properties of the token distribution under the C-delta sharding scheme, measuring the Rouge L scores to assess reconstruction difficulty. Our results indicated that with parameters C, alpha, GEQ8, the Rouge L scores were significantly low, demonstrating effective security against reconstruction attacks. Additionally, we benchmarked Cascade against existing SMPC schemes, such as MPC-Former and Puma, using BERT-Base and BERT large models with an input prompt of 128 tokens. The performance metrics showed that Cascade was up to 90 times faster than MPC-Former and 45 times faster than Puma, confirming its efficiency and scalability in comparison to these existing methods.
What are the notable limitations or potential drawbacks of the Cascade method? How does it fare in practical scenarios where utmost token security is crucial?
The Cascade method has notable limitations, particularly regarding token security. Specifically, while it offers significant efficiency improvements over cryptographic schemes, it does not provide rigorous privacy guarantees, as it is a statistical scheme. In scenarios where utmost token security is crucial, Cascade may not be suitable because comp nodes have access to some token embeddings, which are immediately reversible to their original tokens through a lookup table. This vulnerability means that if individual token security is paramount, integrating Cascade with cryptographic methods like SMPC would be necessary to enhance security. Additionally, the effectiveness of Cascade's security relies heavily on the chosen sharding strategy. Insufficient gaps between token clusters can lead to vulnerabilities against attacks like the vocab matching attack, which could potentially expose sensitive information.